Okay, well, last video on product and quotient rules, at least I think. I probably shouldn't speak too soon. Let's go ahead and just run through a couple more examples and sort of round out our understanding of these two rules. Let's go through a couple that are a little bit more nasty, perhaps a little bit more abstract than the ones that we've gone through previously. The first one, let's go ahead and start out with sine x over e to the x, and I want the equation of the tangent line at 0, 0. Okay. Well, first, let's confirm that this actually goes through 0, 0. Okay, always a good idea. 0, 0, obviously, if you plug in 0 for x in the denominator, it's 1. If you plug in 0 for x in the numerator, it's 0. So 0 over 1 is your output. So when you plug in 0, you get an output of 0, 0, 0. Goes through the origin. Fantastic. Okay, so what we're going to do now is we need to go ahead and, since we have the point, and the only thing that we lack for this tangent line is, of course, the slope, we need to find the slope for this function in general. So dy dx is equal to, well, let's do the bottom times the derivative of the top minus the derivative of the bottom times the top, all of that over e to the 2x. Now this one can be cleaned up very, very easily, and it's kind of convenient that e to the x is the derivative of e to the x. So if I pull out e to the x as a common factor from both terms in the numerator, I recognize the fact that I can now simplify further by canceling out the e to the x that is a common factor in the numerator with one of the e to the x's in the denominator. And I recognize that that is my derivative simplified. Now, if I want to go ahead and find the slope, remember, this is the notation for actually finding the derivative at a particular value, so evaluating it when it's not in function form, when it's in what's called Leibnizian form. Okay, good old Leibniz came up with this form, and it's actually pretty helpful and pretty useful. So we'll go ahead and plug in, and it winds up being cosine of 0 minus sine of 0, all of that over e to the 0. Well, sine of 0 is 0, but cosine of 0 is 1, and e to the 0 is 1, so my slope at the origin is 1. Okay, so I have a point, and I have slope. Well, that means that my tangent line, since x1 and y1 are 0, and my slope is 1, and it goes through the origin, it ought to be pretty easy for me to go ahead and surmise that y is equal to x is indeed the tangent line there. Now, that's okay. Now let's go ahead and do kind of an obnoxious example of the product rule. And I say obnoxious because it has 3 factors. Okay. Now, I know how to deal with the product rule when it has a single factor. When it has 2 factors, however, I'm at a little bit of a loss. Or am I? Because the same principle applies. In the original one, I had 2 factors, and therefore I wound up with 2 terms. Each one of the terms, one of the factors had the derivative taken. Okay? Well, the same principle applies here, but instead of 2 factors, I have 3 factors. So I'm going to have 3 terms. Each of the terms is going to have 3 factors, but in the first term, I'm going to take the derivative of the first factor. In the second term, I'm going to take the derivative of the second factor. And in the third term, I'm going to take the derivative of the third factor. And, okay, this is one of those places where those brackets wind up being very, very helpful. So the derivative of the first times the second times the third. The first times the derivative of the second. Okay, and then the first, e to the x, times the second times the derivative of the third. And that, I sort of messed up right here. That's supposed to be e to the x, okay? Now you can clean this up a little bit. You can factor out an x and an e to the x. So x e to the x that winds up giving me x sine x plus x cosine x plus 2 sine x, or something like that, okay? But notice, 3 factors, 3 terms, all having 3 factors, and in the first term I took the derivative of that first factor, in the second term I took the derivative of the second factor, and in the third term I took the derivative of the third factor. So if I had one with 4 factors, I would, have 4 terms of 4 factors each, and just follow the same principle, okay? Now, let's go ahead and do a couple of quotient ones. Now I know, like I said before, we haven't officially gotten to trig ones yet, but trig derivatives are really easy, and you should remember that the derivative of sine, okay, is cosine, and the derivative of cosine is negative sine. Well, I not only want the derivative on this one, let's go ahead and find the tangent line at pi over 4, 1. Now, some of y'all are looking at that and going, well, that's really neat. That's tangent right there. And of course, if we had actually gotten to trig derivatives, we would go ahead and do it that way. We would go and turn it into tangent, and it would be a one-step problem. Well, let's pretend that we don't know the derivative of tangent, which of course some of you don't. Some of you don't remember. So we'll go ahead and do it by the quotient rule. Now I needed the bottom times the derivative of the top, okay? And I need the top times the derivative of the bottom, and remember the derivative of cosine is not sine but negative sine, all of that over cosine squared. Well, let's go ahead and clean that up and see what we can make of it. And some of you are thinking to yourself, well gosh, I can go ahead and cross out those cosine squareds, at which point you will hear me screaming all the way from Scotland. Okay, now you cannot do that because you cannot cancel terms, you can only cancel factors. To cancel terms is to violate order of operations, and that is a big no-no. But what you can do is you can recognize that that numerator is a fundamental trig ID. It's one of the Pythagoreans. It's equal to 1, and 1 over cosine squared is secant squared. So, what I've really just done is I've really just found out that the derivative of tangent is secant squared. Okay, well that's all kinds of nice. Let's go ahead and evaluate, the derivative at, I just did it again. Okay, it's getting a little late here. We'll go ahead and finish this up though. Now, g prime of pi over 4 is really 1 over cosine pi over 4 squared, right? So if you don't remember what secant of pi over 4 is, you can always just run back to cosine of pi over 4. Now, cosine of pi over 4 is root 2 over 2. But if you don't remember, root 2 over 2 is 1 over root 2 rationalized. Okay? You could, basically, when you were doing the ratios, when we first constructed the unit circle, it wound up being 1 over root 2. And so we rationalized the denominator in order to turn it into root 2 over 2. So if you don't remember, this is the same as that, which is probably pretty good, because if I'm going to then reciprocalize it, right, if I'm going to take 1 over root 2 and take the reciprocal, I know that that's going to be root 2 squared, or 2. So I have my point, I have my slope, and therefore I can do y minus y1 is equal to m times x minus x1. And that, my friends, is the equation of the tangent line of this function at this point. Okay? Now, let's go ahead and move on to another example. This one is quotient rule as well. If we have y is equal to ax plus b over cx plus d, what is the derivative. Okay, now, some of y'all, for some odd reason, get really, really squirmy when we start putting a's and b's and c's and d's, not for variables, but for the constants. Because if I'm dealing with this, this is ax plus b, this is a linear. A and b are numbers, x is your variable. C and d are numbers, x is your variable. Okay? So, in order to actually pull this off, I simply just need to follow the form and just not get scared. Okay? So I need to have the bottom, which is cx plus d, times the derivative of top. Well, the derivative of the top is a, right? If that's linear, then the derivative of the constant term is 0, and the derivative of the linear term is just the coefficient, which is a. And then the top times the derivative of the bottom. Well, the derivative of this linear is the coefficient, which is c. Okay? And this becomes cx plus d squared. Well, when I distribute, I'm going to get acx plus ad minus acx, and that's going to be minus bc, right? Because as I'm distributing this c, I also have to distribute the negative. All of that over cx plus d squared. Now, you need to recognize the fact that these two terms are, of course, additive inverses, so they're going to go bye-bye. And what we have here is AD minus BC, all of that over CX plus D squared. And that would be my derivative. Okay, I think that's good in terms of sort of running over examples. If you need any more examples or you have a specific question, please do feel free to go ahead and email me, guys. Otherwise, we will discuss it at the Skype session coming up on Saturday. Please do read the email that I sent you, I think it was this morning, about sort of learning how to do the QuickTime screen capture video, so that one of y'all can record the Skype sessions that we have on Saturdays for the sake of those people who, because of a swim meet or cross-country meet or something like that, are unable to actually attend those Skype sessions. So I hope that's helpful, guys. I hope that helps you as you sort of start into this week and your teacher starts with Chapter 3. Be looking towards the end of the week for videos on 3.3 and 3.4. And of course, I will, as always, look forward to seeing you on Skype this coming weekend. Bye.